The following introduces the application in forest fire simulation. Generally, process of making forest fire information system can be divided into three parts. The first is the preparation before fire. The second is finding and acting on fire, and then putting out the fire in fire. The third is the post-disaster treatment after fire. The system mainly do some applications on the emergency decision and integration of information in fire. This one. In the prediction of path of forest fire, there needs some data beforehand, including land plate, road network map, vegetation map, and trees distribution. The following shows the fire behavior. The left figure shows the situation of fire burning. The right figure introduces some parameters, including flame length, flame height, and flame angle. The angle will change as the wind speed. As the wind speed increases, the angle will become small. The figure bottom shows the depth of fire. Next, let's see some factors about the spread of fire. The first is the spread rate of a free-burning wildland fire. The spread rate means the speed of moving of front-end fire, also meant the moving distance in each minute. The unit is meters per minute. The second is fireline intensity. This means the accumulative energy in a distance. By using this value, user can separate the degree of fire intensity. As the value gets higher, the intensity gets strong. After getting the fireline intensity, the system can get flame length. As the length gets long, the fireline intensity gets high. The flame length also has relation to resulting in the burning of crown tree. By the research data, general shape of burned area is ellipse. Take the left side figure for example. If the direction of wind is like that shown left, the burnt area will be like this here. The detailed introduction is that the yellow point is ignition point. The direction of wind is to north. This is the heading fire. The fire here is more strong. This is the backend fire, and the gray area here is the burnt area. Among all the factors about the fire spread, one important factor is the wind speed. The speed for estimation is mainly the mid-frame wind speed. The wind here is mid-frame wind. This and these are not the mid-frame winds. This is defined as the velocity of the wind in meters per second, taken at the mid-height of the frames. When the speed is high, the spread is fast also. The speed may be affected by the model of fuel, vegetation, and terrain. For example, as the plains are dense, or the terrain has obvious height fluctuation, the moving of wind will be blocked. Therefore, the speed will be slower. As the region is plain, the wind speed will get higher. Another factor is the slope. The research shows that the slope has much affection on the fire spread. The main affection is that the spread rates to top and to bottom are different. The rate to top is faster than to bottom. This means the fire spreads mainly to top. Therefore, if the ignition point is on top of the mountain, the rate of spread will obviously slower than that the ignition point is in the bottom of mountain. The shape of the situation of the whole fire is usually an ellipse. If the situation is in plain terrain without wind, the shape of fire spread will be a circle. Next, let's see the 5 shapes. 1, 2, 3, 4, and 5. As the length to breadth ratio increases, the wind or slope increases also. In other words, the shape 5 is the situation that the wind speed is very high or the slope is very steep. The movie left shows the real situation of fire spread. Here, the wind direction is to right up. This is the heading fire. The heading fire is very fierce. This is the backing fire. The backing fire is weak. Farsight, F-A-R-S-I-T-E, is the software developed in USA Forest Fire Lab. The simulation is based on geographical information system. By using Huygens principle, it shows the spread in ellipse shape. The Huygens principle can be described simply that each frame can be subdivided into multiple segmental small flames, and each small flame can be taken as a ignition point. The spread begins from each ignition point, and then the collection of total burnt area of each small flame is the final burnt area of the flame. In Figure B, different shapes of spread are generated by different speed and fuel mode, and then the shapes of spread will be different. Common fire has two kinds. One is surface fire. The surface fire is meant the fire begins to burn from the surface of ground, the roots or the bottom of trees, and spreads along with the ground. The figure shows the surface fire. After a period of time of burning on the surface of the ground, the fire is as strong as that in some level, and then the fire may burn the tree crown, which is the place on that the leaves are. Here. Once the crown fire is generated, the fire will spread fast by the wind along with the crown tree. This kind of forest fire is hard to be extinguished. Therefore, this kind of fire gets more concerns than other kinds of forest fire. The prediction and extinguishment way of fire are worth to be investigated. To simulate the behavior mode of forest fire, the three factors must be taken into consideration. The first is fuel. Fuel is the litter, dead fallen trees, weeds, and shrubs that most vulnerable to fire, positioned in the surface. For example, the crown tree branch is the source of crown fire. The second is weather. These are the relative humidity, change of temperature, and winds that affect the spread of fire. The wind speed is the key factor of spread rates of forest fire. The third is the terrain. The change in terrain generates several kinds of microweather. For example, the fire in steep slope spreads to the top much faster. The following introduces the parameter of system. According to the discussion before, the input factors include weather, terrain, and fuel. The weather includes speed and direction of wind. The terrain includes the degree and direction of slope. The fuel includes fuel load, heat, depth of fuel, surface area to volume ratio, density of fuel particles, fuel humidity, and extinction humidity of fuel. The extinction humidity of fuel means when the humidity of the air is higher than the extinction humidity, the fire will rarely be burned. Therefore, when the extinction humidity is high, the fire is easy to be burned. After the input of factors and calculation, the full output will be got as in the figure above, including spread rate, reaction intensity, fire intensity, and length of fire. After getting the fire intensity and length of fire, user can understand the situation of burning of the whole fire. Next, let's see the spread rate. This is the core of the whole analysis. The equation is called Rothermore's spread equation. The equation has several parameters. This one is the reaction intensity. The reaction intensity has a relation to the fuel reaction rate, pure fuel load, energy released in each unit fuel, and damping factors of mineral and humidity. The parameter of this one. This is a transmission rate of flux. The transmission rate of flux represents the amount of energy released and spread to the neighboring fuels. And this one is the density of fuel. The density of fuel represents the load and depth of fuel. This one is the effective burning coefficient. The effective burning coefficient represents the ratio of heated fuel being burned. And this one is the energy needed for burning fuel. The energy needed for burning fuel represents the humidity of fuel. The last two parameters are effect of wind and effect of slope. The effect of wind means the mid-frame wind speed, which is the affection near the surface of the ground. Although the size of fuel particles is another important factor, as the size is small, the particle is easy to be blew for, increasing the spread rate. The other is fuel rate of fuel blend. As the fuel rate gets high, this means the fuel is more dense and then the flow of air will get bad. Therefore, the effect of wind becomes small. Besides, the effect of slope has much relation to the slope of the mountain. After seeing the system parameters, including the introduction of input and output, let's see the prediction of fire spread. This part includes the direction and range of file spread. First, the system divides the whole forest into a non-overlapping grid space. Each grid has the terrain information. The terrain information means the related information about GIS, like fuel, weather, spread speed, and direction, and so on. After the user sets the ignition point, the system will begin to simulate the file spread. The available directions of each grid have 8, as shown in this figure. The degree starts to change from north. Here, this is 0, clockwise, to here is 45, 90, 135, 180, 225, 270, 315. In the spread direction of fire, it is mainly decided by the wind direction and slope. Take this figure for example. This is the vector of wind. This is the vector of slope. And this is the combination of the two vectors. Okay, this is also the direction of the spread rate of the fire. In other words, in this direction, the fire spread is the fattest. The spread rate is the length of the vector. According to this rate, the system can get the rates in other directions. After the completion of spread rate, the system needs to separate if the thing in this grid will be burned. This is mainly decided by the fire line intensity. When the intensity is bigger than 45 kilowatt per meter, the thing in this grid will be burned. As mentioned before, the shape of fire spread area is ellipse. In this figure, the ignition point is here. The direction of wind is to east. By the wind speed and maximal spread rate, the system can get the perimeter of the ellipse. The semi-major axis, half minor axis, and half focal distance. By the three parameters, the system can get whole ellipse. The spread rate of heading fire is B plus C. The lateral spread rate of fire can be estimated by the ratio of distance between the ignition point to the lateral. and 2 B plus C. The spread rate of baking fire is B minus C. After getting the area of the ellipse, the system will get the vector of each direction, comparing to the maximal spread rate R here, and then get the ratio of each direction to understand the situation of the whole fire. Next, the system begins to do analysis and simulate the fire spread. In the beginning, user needs to define the size of a grid. For example, a grid with 15 multiplying by 15. After definition, by the speed and the distance between two grids, the system can get the time of moving from the grid to the neighboring. The definition of the thing of grid is burned out is that all the things of neighboring 8 grids are all burned. Besides, the system admits user to modify the spread rate dynamically, including wind, speed, and direction. Then, the needed time can be got, and the situation of fire spread will be modified. In the definition of size of grid, user needs to concern the vegetation, terrain, and calculation time. If the size is set too small, the calculation load will be too heavy and the calculation time will be too long. If set too large, one grid may contain different types of vegetation and the setting of parameter will be distorted easily. If the fuel of the grid has chrome tree here, the system must separate if the fire will become chrome fire. The judgment is based on comparing with the critical surface fire intensity, which is taken as the threshold. When the fire intensity is larger than the threshold, the chrome fire will be generated. After generation of chrome fire, the burning type will be decided by the density of leaves and the height of the tree. If the fire turns into chrome fire, the spread rate and final intensity of chrome fire are different from that of surface fire. The flying distance of ashes of chrome fire with different types are not the same, and the ranges of fire spread are also different, as shown like the two figures here and here. When the arrangement of trees is denser, the final intensity will become fiercer and the spread rate will become faster. Concerning the generation of spotting, the possibility, intensity, height of ash spotting are affected by the types of fuels, and the size of particle of ash is also the important factor. As the size is small, the distance of spread will be larger and then the spread rate will be faster. Relative humidity in the air also affects the generation of spotting. If the humidity is less than 25%, the spotting almost 100% happens. The temperature and wind speed are also important factors. When the temperature is above 60 degrees Fahrenheit or the wind speed is over 20 miles per hour, the spotting almost 100% happens. If the situation has been generated, the firelight intensity is hard to be estimated since the affection factors become more complicated. Ash has possibility to be ignited after being on ground in some proper situation, including enough fuel easy to be ignited, loose fuel, fuel with few water, enough wind speed, high temperature, and low humidity. Besides, the type of country and vegetation that the ash is on must be taken into consideration, and then the situation of spotting can be made sure. The figure records the 13 models. The system completes the simulation mainly by the parameters of the model. These kinds of data are got from the experiments, including the parameter of type of fuel and the values about the fuel. In different kinds of plants or fuels, we do some tests in the same system environment. The setting of environment is mid-frame wind speed 5 miles per hour and the dead fuel moisture content and live fuel moisture content. The dead fuel moisture content means the moisture of the fuel that is burned out. The live fuel moisture content means the moisture of the fuel that is still alive in the air after burning. Here, the dead fuel moisture content is set at % and the live fuel moisture content is set 100%. The affection of wind speed and direction on forest fire is global. As the wind speed gets larger, the air is easier to be transmitted into the fire to increase the growth of the fire. Therefore, the wind speed and direction are important factors of spread of fire. Humidity is also an important factor that affects the fire intensity. Besides, the humidity among one day is not constant and may change a lot. For example, among the time from 10 o'clock a.m. to 2 o'clock p.m., the radiation of sun is strongest and the temperature is highest. Therefore, the wind speed is high, the direction is unstable, and then the extinction of fire is harder. In the contrary, among the time from 4 o'clock to 6 o'clock a.m., the temperature is low, the humidity is high, and the wind speed is low. Among this time, the extinction of fire is easier. In other words, this is the better time for extinction of fire. Of course, the rainfall is the best way to extinguish the fire. The 13 types of models are based on the data from the forest fuel type in USA. Therefore, the model has some difference from the model in Taiwan. If the model is going to be applied in Taiwan, the data must be updated from the forest database of Taiwan first. In this way, the prediction and simulation of the fire spread by our system will be correct. The records introduced above are the data about the 13 types of fuel models. Next, let's show the simulation of fire spread by using the virtual data created from our system. Here, the first data needed to be set is dam layer data. The dam layer data records the height and low of the terrain which affects the fire spread. Next, set the wind speed and the direction. This is the wind speed and the direction. The wind speed is generally set 2.22 meters per second according to the research. Wind direction is set by angle. The system sets the right east 0 degree, the right north 90 degree, the right west 180 degree, and the right south 270 degree. Besides, user can also set if some region is burnable. If the research on some region is so hard that the getting of data is impossible, the system will add the value into the region by interpolation. Before simulation, user needs to add some ignition points. The display here changes in 5 minutes. In the figure, the red part is the region in burning. The black part is the region that is burned out. This is the situation in 5 minutes. This is the situation in 10 minutes. The figure shows that the heading fire is fiercer than the backing fire. This is the situation in 15 minutes. This is the situation in 20 minutes. This is the situation in 25 minutes. The figure shows that the shape of burning region is ellipse, and this is the situation in 30 minutes.